Hey, Matt Matherson here with Math Madness. Thank you so much for joining us and being a part of this illustrious program. Well, you know how we feel about it. Thanks for being here, and we really do appreciate it. Well, we've been dealing with limits previously using the L'Hopital rule, and we've been seeing how that can really shorten the situation when we're trying to find limits of rational functions, I should say, when we're dealing with fractions. Well, today we're going to take it up a notch. There will be no L'Hopital to help us out here, but I feel confident we can still get through this. So this is a polynomial. It's a rational function because we're dealing with fractions, obviously. And if you haven't dealt with polynomials before, it's just because we have two terms here. More than one term is a polynomial. We've got a 5x being raised to the 3, and that's separated by this operator of addition. And then we've got the 7x over here on the other side of the operator. Okay, well, before we even get started, I'm just going to go ahead and tell you the answer, and it's 0. Okay, so let's just go ahead and say 0. It's not a real big deal because what we need to know is how do we get to that answer of 0. So let's just go ahead and deal with this right now. Okay, well, I can get rid of the 7x because I only have to focus on the terms with the highest exponent, and that's just our first term here, the 5x being raised to the 3 on the numerator and the 2x being raised to the 8 on the denominator. So I can cross out the positive 3 and I can cross out the 7x. Before I do, though, you'll see people just cross it out and move on, and that's fine, but I'm going to explain to you why that's actually taking place, the mechanics and operations mindset behind all of it. So let's go ahead and say that we plug in the value of 10 for our x. So if I take 10 and I multiply that by 7, that gives us obviously 70. If I do the same thing over here, plug in a 10, well, that 10 is being raised to 3, isn't it? Right? 10 times 10 times 10 is 1,000. So then I take the 1,000 and I multiply that by 5, and I have 5,000. Case in point, this grows exponentially faster. There's the pun of the day. Exponentially faster than what this does over here, because this only has an exponent of 1, doesn't it? Yeah, that's it. So that's why we can do away with these lower terms that have these lower exponents. Okay. That said, let's go ahead and deal with what I've just laid out, and we only have to deal with the 5x3 over the 2x8. So let's take this as the limit x approaches positive negative infinity is what we're being tasked with finding. We've just got our 5x to the 3rd over 2x to the 8th. A little basic algebra. Again, don't ever underestimate algebra. She is our friend. I can get rid of all the x's on the numerator, can I? Well, I just did, so I can. What about the 8? Well, I can get rid of the, take away 3. That's going to leave me 5 x's on the bottom. Should. All right, so now what do we have? Well, we've got 5 in the numerator. It's not going anywhere. I've got 2x being raised to the 5th now, so we can kind of see that this bottom part is going to get a little bit bigger. Let's go ahead and take the limit of this new rational function here as x approaches positive negative infinity. Again, we've got 5 on the numerator, and I've got a 2x being raised to the 5th here on the bottom. Again, we said the numerator is not going to go anywhere because there's no more x's, so it's going to say 5 and 5 and 5 in perpetuity. That's wonderful for us. Now, the bottom's not exactly like that, though, is it? If I plug in our infinity here in x, then I've got infinity raised to 5, right? I've got infinity 5 times, and then I'm multiplying that by 2. So I know my denominator is going to get really big. I know those are some sorry infinity signs. I'm not an artist. What can I say? Nevertheless, we've got a small number being divided by a really big number. Sir, infinity. That gives us a limit anytime the number on top is smaller than the number on the bottom. Yeah, that gives us a whopping 0 limit. How did I know that? Just by looking at this initially. Here's the trick. Your exponents. If I've got a smaller exponent on the top than the numerator, or the numerator is smaller on top than the denominator, like here in 8, I know my limit is always going to be 0. We don't need the L'Hopital rule for this. Relatively simple. Well, that's all the time we have for here on Math Madness. I am Matt Matherson. I'm going to see you guys really anon.